Hello, my name is 189b-Benyahia, and I'm going to be talking to you in this presentation about some simulation results that show the formation of granular jets. So as you can see here, we can predict a taller jet under atmospheric conditions and a small jet under a complete vacuum. So this jet formed by an intruder that hit a bed of fine particles, similar to when you throw a stone or a rock to a pond. You see that there is a cavity that forms, and then the cavity collapses and the jet forms. And this is also seen experimentally with fine powders, as this experimental pictures show under 1 atm and under increasing vacuum. So we see under 1 atmosphere that there is a tall jet, and this jet decreases under vacuum conditions. And these results were shared courtesy of Professor Yager at the University of Chicago. So this is what I'm going to be talking about today. As a short introduction, granular jets, the same as water jets that form when you hit a stone on a pond or lake, they form when an object impacts a bed of fine granular material in this case. So these jets were observed experimentally, but they have not been computed in simulations, and attempts were made, and I will talk a little bit about that in this presentation. So this numerical study reproduces qualitatively what experimentalists see, that a taller jet extends vertically from vacuum condition to atmospheric conditions. So a simple explanation is based on friction between contact between particles, and that is provided here to explain the experimental observations. Other effects such as initial intruder velocity and its diameter are also in qualitative agreement with experimental observations. So the approach that we use a Lagrangian discrete element method to track particle motion. And in this case, we have about 150 million particles, along with a soft sphere collision model to resolve collisions between particle-particle contact and also between particle-wall contacts. A fixed mesh CFD to model the flow of air was also used with highly resolved mesh, about 4 dp, which resulted in 3.5 million fluid cells. The shape of the large intruder, and this is very important, the shape of the large spherical steel intruder was approximated by gluing particles of the same size as those that make the bed material, which are 100 micron. This was done for efficient collision and neighbor search algorithm. The bed material was also first fluidized to obtain a random initial state of particles. This is similar to how it's done experimentally, and I will show you some video of the fluidization of these type A particles. Simulation conditions. So we have a 3D system that contain 150 million particles. Those particles are 100 micron in diameter and 1500 kilogram per cubic meter density. When air is used at ambient condition, and the flow of air is simulated using a very fine mesh, as I mentioned before, about 4 dp, resulting in 3.5 million fluid cells. Friction coefficient, unless otherwise mentioned, was used about 0.2, and the restitution coefficient for particle-particle and particle-wall contacts was the same as 0.9. The spring constant has this value. So the bed was first fluidized at 3 UMF to obtain initial particle positions that are random to imitate a real experimental setup. And the next slide shows just that. So here I will play this video, and you have at the bottom a gas distributor, uniform gas distributor, and you can see very small bubbles forming at the bottom of the bed. They coalesce as they move upward, and then they burst here on the top, on the freeboard. The same thing can be seen in 2D slice. So the 2D slice shows the behavior on single slice, but the best view of obviously is the one that looks at the isosurface here. Let me just play it again. So the isosurface allows us to look at the flow of bubbles, three-dimensional flow of bubbles inside the bed. What usually you see as an experimentalist is just at the top, bubbles bursting. And at the wall, as you can see, there's very little things going on near the wall. So you won't see much, very few bubbles from time to time. So if you can have a look inside and look at these bubbles, you can see the small bubbles that are typical of of type A powder when they're fluidized by air. So type B powders will result in much larger bubbles. So this is, again, in qualitative agreement. And we fluidize this, so then we turn off the gas inlet and then we let it set. And then we run our simulations, which are of interest in this. So in this presentation, my interest is in the formation of granular jets. So we have an intruder, initially in this case set at the velocity of 2 meters per second. We don't just drop it at an initial zero velocity. Here initially it has 2 meters per second. So when it reaches the bed, it will reach at a higher velocity, larger than 2, because it falls under its own weight. And then when it goes inside, as I will show you, I'm playing the video here, let's just play it. So it will form a cavity. This is both under 1 atmosphere and under complete vacuum. So it forms a cavity, then this cavity walls collapse. And you notice here the color is black of the jet. Black is 1 meter per second and more, the vertical velocity, and -1 is white. So the grains that fall down have a white color. So we have to play it again one more time. So when the intruder reached the bottom, as you said, as the walls collapse, there is a bubble that forms at the bottom. And this bubble, the air from this bubble keeps going up and fluidizing this section. As you can see, particles are moving here, and that doesn't happen in the case of a complete vacuum. So because there's motion of particles here, there's very little friction. That's what allows, in my opinion, the jet to climb higher, because there is less resistance when these two walls collapse and the jet is generated. By the way, obviously the jet is generated in both cases, both under 1 atmosphere and under vacuum conditions. But in this case, in the case under one atmosphere, because the particles here are well fluidized, there's very little contact and frictional contact. So the jet has a higher velocity. So it's not slowed down because of frictional force. In this case, there is no air to fluidize the grains below the jet, and the particles are stuck in contact, and once they're in close contact, then friction is significantly important. We check that in the next slide. We look at the effect of particle sliding friction. So as we lower friction, and both of these results were obtained under complete vacuum. So as we reduce friction, we see that we obtain a taller jet. So you can reduce friction by reducing it for vacuum or by introducing air. So when you introduce air, the fluidizing air here causes lowers the apparent frictional force between particles because it fluidizes them. So I say here that friction plays a major role in the formation of granular jet. The presence of air helps to fluidize particles, diminishing the effect of that apparent friction. So next I will show you the effect of intruder initial velocity. So as we increase the intruder velocity from 0 to 4, we see that as soon as the intruder hits the bed, there is a crater that forms, and then it generates a jet. So this jet is taller as the initial velocity of the intruder increases. Except at 4 meters per second, what happened at 4 meters per second, the intruder hit the bottom of the bed and bounced back and interfered, as you can see here, with the collapse of the walls. So it actually interfered with the formation of the jet. But in general, we see that there is a continuous increase the jet height, the granular jet, as the initial velocity of the intruder is increased. One of the very important parameter that I looked at was the intruder diameter. So as we reduce the intruder diameter, by the way, all the previous simulations were done with 1 centimeter intruder. When we reduce it, as you can see, that resulted in the smallest jet, granular jet. And I say this is important because when I look at the literature, previously published research were not able to show that there is a tall jet forming in accordance with experimental observations. All what they showed was a very tiny jet like this one. And I think it's because they use a small intruder. The reason they use a small intruder because of issues you have with intruder particle contact. So as soon as the intruder hits the bed, the interaction, because these have a hugely different diameter, the intruder has a very large diameter compared to those particles in the bed. The search algorithm, which is usually grid-based, can create a huge amount of neighbors in a neighbor search, in a neighbor list. Therefore, the memory requirement would be humongous. So one very simple way to deal with that, as I'm doing here, was to consider the intruder as made of glued particles. So I think as I search in the literature, this is the first time glued particles were used, this technique was used to resolve an issue that we have with the large size disparity between contacting particles. In this case, the intruder and the bed particles. So by gluing particles and to form the intruder, small particles, then we solve two problems. We solve the problems of contact between the intruder and the bed particles, and we also now can use a very fine mesh. So we actually mesh the bed and the intruder, and we resolve the flow inside the intruder. I mean, since the intruder is a dense, so there's almost no flow through the intruder, but air can actually flow through it, but in general it tends to avoid it, so going around. We can even calculate the drag around the intruder, similar to what IBM does, but with less precision in this case, but still that's possible to do. So in conclusion, coming back again to the main point of this talk is that the resolution of intruder particle collisions and airflow was facilitated by gluing small particles to form the large intruder. This is by no means the only way of doing this, of solving this problem, but this is the simplest, in my opinion. It was the simplest way to solve this problem. This allowed me to simulate granular jets that are in qualitative agreement with what experimentalists observed, especially Professor Jaeger at the University of Chicago. He has many nice experimental videos that I encourage you to look at if you're interested. In terms of videos, there are more animations, more videos are available online at the INECR website. So this is the paper that I just published, titled the same title as this talk, which is simulating the formation of granular jets. I encourage you to download them so you can see the videos in much more crispy details. You can see the videos that I just showed you, as well as many more. So there are a lot of animations that are available there that you can use them for any purpose, for example, education. The paper also contained detailed quantitative analysis of simulation data that I'm not talking about today. So this is all available at the INECR website. So even if you don't download the paper, you can still download for free the animations, and I encourage you to do that. And thank you very much for your attention and for your time.